Welcome to this video on trebuchet release mechanisms. Here I will discuss how to set your sling release based on either sling angle or arm release angle. I will also discuss the advantages of both. This video should be useful if you're interested in hanging counterweight and floating arm trebuchets. It will also show you how to go off the beaten path. Part 1. Angle dependent release. Shown here is a typical angled pin release mechanism. This setup uses an angled pin to keep the sling loop in place until the time of release. While the trebuchet itself is a fairly complicated mechanical system, the release point of the loop is a fairly straightforward statics problem. To elaborate, we draw a free body diagram showing the forces on the sling. This includes the force of tension from the sling and the normal force from the pin onto the loop. The force from tension is broken into components, parallel and perpendicular to the pin. Lastly, there is the force of friction. While the system does undergo great acceleration, the loop's mass is insignificant. This causes the M8 terms to go to zero, enabling us to view this as a statics problem. From there, we balance the perpendicular components, relate force of friction to the normal force, and write out the parallel component of tension. At release, the parallel component of tension becomes greater than the force of static friction. Thus we work out the parallel forces to find the critical angle. Looks like the tension drops out and release angle depends only on the coefficient of friction. To summarize, this mechanism yields sling angle triggered releases. The sling release angle can be set by adjusting the pin angle. This has the obvious advantage of simplicity. It's also relatively easy to tune this type of release to your trebuchet's sling stall point, where most of the trebuchet's energy is in the projectile. I cover important trebuchet stall points in another video. Part 2. Arm angle determined sling release. Let's use a multiple rotations trebuchet with a free hanging sling as an example. I am drawing a front view of the arm. There are bearings on the ends, allowing the arm to rotate freely. On the left there is a pulley wheel driven by a falling counterweight. This is connected to the arm by a drive shaft, placing the arm a safe distance away from the counterweight. This design uses a fishing reel style release mechanism. To the right of the arm there is a stationary cylinder, which the arm winds string around as it rotates. This string is connected to a pin, which holds the sling loop in place. As the arm rotates, the slack in the string decreases until it pulls out the pin, releasing the projectile. The release angle of the arm can be modified by rotating the cylinder a few degrees and locking it back in place. Here is a quick mock-up of the arm, demonstrating how the release mechanism works. Next, a clip of a working device. There are complications. The trebuchet undergoes multiple sling stalls. At these points, the arm almost stops, and most energy is in the projectile, making for a very desirable release point. Unfortunately, a purely arm angle triggered release may produce mixed results if you aren't careful. Hybrid release systems may be more stable. Here is a free hanging sling design that uses both arm and sling angle to trigger a sling release. Simulations indicate that folded slings are probably more efficient and more controllable than free hanging slings. Here is one possible design. Thank you for watching. If you like this, check out my trebuchet physics video.